Hello, my name is Dr. Kenneth Watanabe, and today I will go over the definitive proof of the Goldbach conjecture. Goldbach's conjecture is one of the oldest and best known unsolved problems in number theory. It states that every even natural number greater than 2 is the sum of two prime numbers. This conjecture was first proposed by Christian Goldbach to Leonhard Euler in 1742. And since then, it was widely believed to be true. Euler responded that this conjecture is an entirely certain theorem, in spite that I am not able to demonstrate it. The first thing I did to prove this conjecture was to write a Python program that calculated the number of prime pairs that add up to n for even values of n up to 50,000, and this is what the curve looks like. Herzog and Silva confirmed that Goldbach's conjecture holds true for values up to 4 times 10 to the 18th. So it looks like it's true, but a graph is not a proof. So here are some functions I use to prove Goldbach's conjecture. P sub n is a set of pairs xy such that x and y are odd and x plus y equals n. Vertical bars around the P sub n is the number of pairs in the set P sub n, and this actually equals n over 2 minus 2. Okay. L sub x is the largest prime number strictly less than x. Capital K sub n is the number of pairs of P sub n where either the x or y is composite. W sub n is a fraction of pairs of P sub n where x and y are prime. And capital Pi sub n is the number of prime pairs xy such that x plus y equals n. We can call this the prime pair counting function. And pi star of n is a close approximation to the prime pair counting function. All right, so to prove the Goldbach conjecture, I use the sieve of Eratosthenes. This is an ancient algorithm to find prime numbers less than n. And the way it works is starting with a list of positive integers greater than 1, you take the first number in the list, which is 2, and eliminate all the numbers divisible by 2 up till the endpoint. In this case, n is 27. Then you take the next number in the list that has not been eliminated. That would be 3, and you eliminate all the numbers divisible by 3. Then you take the next number in the list, which is 5, and you eliminate everything that is divisible by 5. And then there's no need to go beyond 5 because the next number in the list that hasn't been eliminated is 7. And all the numbers divisible by 7 have already been eliminated. So, for example, 14 is divisible by 7, but it's already been eliminated because it's divisible by 2. 21 is already divisible by 3. And the next number, the first number that is divisible by 7 that hasn't been eliminated is 49, but the endpoint is 27. Okay? So you only have to go up to the square root of the endpoint, which is around 5. All right. So what I did was I applied the sieve of Eratosthenes to pairs. So for n equals 60, what I did was I paired up all the numbers that add up to 60. There's 28 pairs in total, and here they are: 357, 555, 753, etc. And I eliminated all the pairs where either the x or y are divisible by 3. So this pair is eliminated because 57 is divisible by 3. This pair Both 9 and 51 are divisible by 3. 15 and 45 are divisible by 3, etc. So about 1/3 of all these pairs was eliminated. Notice where the x-coordinate is divisible by 3, the y-coordinate is also divisible by 3. Now, if we chose a value of n that is not divisible by 3, such as n equals 62, and did the same thing, we'd get a different result. For instance, here, 557, 57 is divisible by 3, and here, 953, the 9 is divisible by 3, 1151, 51 is divisible by 3, etc. And in this case, we're eliminating about 2/3 of the pairs. Twice as many as if n is compared to where n is divisible by 3. Okay, so here we see every set of 3 we're eliminating 2 pairs. All right, so we can postulate that relatively more pairs are eliminated when n is not divisible by 3. Okay, next we eliminate pairs that are divisible by 5. So if we look at n equals 60, we got 1545. Both the x and y are divisible by 5. 2535, both x and y are divisible by 5. 3525, both coordinates are divisible by 5. And we'll eliminate about 1/5 of the numbers. If n is not divisible by 5, if we go back to our example, n equals 62, here 55 is divisible by 5, and here 15 is divisible by 5, here 45 is divisible by 5, and here 25 is divisible by 5. So in this case, when x is divisible by 5, the y is not divisible by 5. So if we look, we are eliminating 2 pairs for every group of 5. All right. So here we're eliminating twice as many numbers compared to when n is divisible by 5. So we can postulate that more pairs are divisible by 5 when n is not divisible by 5. And then we can do the same thing with 7. Here, 1349, the 49 is divisible by 7. 2141 is divisible, the 21 is divisible by 7. And 2735, the 35 is divisible by 5. So here, for every 7, we're eliminating about 2 pairs. Okay, so every group of 7, we're eliminating 2 pairs. So basically, to eliminate the most number of composite pairs, n must be a value that is not divisible by any odd prime number less than the square root of n. In other words, values of n equal to 2 to the I, or n equal to 2 to the I p, where p is a prime number greater than the square root of n. These values of n have the most pairs with a composite x or y value. So we can postulate that values of n with the fewest prime pairs are values of n that are not divisible by a prime number less than the square root of n. So the next thing I did was I plotted the number of composite pairs for different values of n. And this top line here, this is values of n that are equal to 30 times a prime number. Okay, and it's high on the curve here. This dark line here, these are values of n equal to 6p. In other words, values of n that are divisible by 3. This yellow line here, this is values of n that are values of n that are equal to 10p. So values that are divisible by 5. And this orange line at the bottom, these are values of n that are not divisible by a prime number less than the square root of n. So these are values of n equal to 2 to the ip or just 2 to the I. And notice it lies right at the lower boundary of this curve. Okay, this is the lower bound on the number of pairs that add up to n. Okay. So next we have to calculate a function that approximates this lower bound. So let's start with finding the number of pairs where either the x or y coordinate is divisible by 3. We'll call this k sub 3 of n. Okay? And let's choose an n that is not divisible by a prime less than the square root of n. So let's choose 62. It's a good number. And here are all the pairs that sum up to 62. And if we eliminate the ones that are divisible by 3, 57 is divisible by 3, 9 is divisible by 3, 51 is divisible by 3, we end up, if we just look at the x component, we will eliminate the number of pairs of p sub n minus 1 divided by 3, and it's the floor of this value here. Okay, the number of pairs minus 1 divided by 3, and we take the floor of it. And the reason why we have to subtract 1 is because we're not counting this pair, 3, 59. Okay, and then to get the total number of pairs for both x and y, we multiply by 2. Okay, so we get this equation here, k sub 3 of n is 2 times the floor of p sub n minus 1 divided by 3. And as n goes to infinity, this k sub 3 of n approaches 2/3 p sub n. Okay, so that's the number of pairs that are divisible by 3 for values of n that are not divisible by 3. And if we subtract that from the total number of pairs, that's the number of pairs that are not divisible by 3. And we'll call this capital pi sub 3 star of n. All right, and that would equal the number of pairs times 1/3. Okay, and we can do the same with 5. About 2/5 of the pairs are divisible by 5, but since 2/3 of them have already been eliminated, the number of pairs divisible by 5 and not 3 equals the number of pairs of n times 1/3 times 2/5. Okay? And if we subtract that from pi sub 3 star of n, that will give us the number of pairs that are not divisible by 5 or 3, and that equals p sub n times 1/3 times 3/5. Okay, for very large n. Okay, and then we can do the same with 7 as n goes to infinity. This is how many are divisible by 7 and not 3 or 5. We subtract that from pi sub 5 of n, and we get the number of pairs not divisible by 3, 5, or 7. Okay, and that's p sub n times 1/3 times 3/5 times 5/7. So the number of prime pairs less than n will be equal to the number of pairs of p sub n times this product, p equals 3 up to the square root of n of p minus 2 over p, where this product is over prime numbers. All right. So if we define this product here as another function, w sub n, the number of prime pairs of n simplifies to the number of pairs p sub n times w sub n. All right. So this is an approximation to the number of prime pairs for values of n not divisible by a prime number less than the square root of n. All right. And the next thing I did was I plotted this pi star of n, and this is what I got. This blue line here, this is the actual prime pair counting function, the actual number of prime pairs that add up to n. And this red curve here, this is my pi star of n. Okay, and it kind of underestimates the prime pair counting function a little bit for n less than 1,000, but for very large n, as n increases, the two curves they line up right on top of each other. All right, so it's looks like it's a pretty good approximation for large values of n. If you look closely at this curve, you notice it's quite jagged. You know, it has this sawtooth shaped. And the reason being is when n goes from a prime number squared minus 1 to a prime number squared plus 1, a new term is added to this w function. You know, this L of the square root of n. It's constant until we cross over a prime number squared. And when we do, we add another term here. So that's why we have this zigzag shape. Okay? And for points between where n is a prime number squared plus 1 to the prime number squared to the next higher prime number squared minus 1, the w function doesn't change. Okay? So we end up with pi star sub n is basically the number of pairs times a constant between points B and C here, and the slope is equal to the number of pairs. Okay, so this will slope upward with the number of pairs, and then when we cross over to the next prime number squared, the curve will drop. Okay, so if we can prove that for all prime numbers p sub I and p sub I plus 1, the next higher prime number, that point D is greater than point B, that will prove that the curve goes up indefinitely. Okay. So for what we'll do is we will prove that for points D and point D will always be greater than point B. And to do this, we must look at the w function and see how it changes when it goes from p sub I squared to p sub I plus 1. And if you look, we know that w of p sub I plus 1 squared plus 1 equals p sub I plus 1 minus 2 over p sub I plus 1 times w of p sub I squared plus 1. Okay, so we can get w of p sub I plus 1 squared in terms of w of p sub I squared. Okay, so to prove that point D is greater than point B for all primes, we'll use induction. So base case, p sub I equals 3. We plug p sub I into our equation here. Pi star of 3 squared plus 1 is pi star of 10. And this equals 3 times 1/3, and that equals 1. All right. So we know the base case is true, that this pi star of p sub I squared plus 1 is greater than or equal to 1. Next, we'll assume that this pi star of p sub I squared plus 1 is greater than or equal to 1. and prove that pi star of p sub I plus 1 squared plus 1 is greater than 1. All right, so we're going to prove that this is greater than or equal to 1. So this equals the number of pairs of p sub I plus 1 squared times w of p sub I squared plus 1. And w of p sub I plus 1 squared plus 1 is equal to this, so we just substitute for this here. And then we simplify, and then we get this equation here. Okay, pi star of p sub I plus 1 squared plus 1 equals this mess here times pi star of p sub I squared plus 1. Okay, and we're assuming that this is greater than 1. So we have to prove that this term here is greater than 1. If this term is greater than 1 and we're multiplying it by a number that's greater than 1, then the product is greater than 1. All right. So to prove this is greater than 1, we rearrange this inequality and we end up with this here. And to minimize this left-hand side, we want to minimize this left-hand side to make sure that the inequality holds true. So the lowest, to minimize it, we have to minimize p sub I plus 1. And the minimal value that p sub I plus 1 can be is p sub I plus 2. All right, that's the lowest p sub I plus 1 could be, is p sub I plus 2. So we substitute p sub I plus 2 for p sub I plus 1, and we simplify, and we end up with this equation here. Okay, 2 times p sub I minus 1 squared minus 4 is greater than 0, and this inequality holds true for all p sub I greater than or equal to 3. And this proves that for any prime number, point D is always going to be greater than point B. Okay, and a similar proof can also be done to prove that point C is always greater than point A on the graph, and thus this proves that my function pi squared of n increases indefinitely and is always greater than 1. All right, and this proves that Goldbach's conjecture is true for all values of n, and that the number of pairs actually increases as n increases. All right, so I showed this proof to another mathematician, and there's just one little problem. Okay, this pi star sub n is not equal to the actual prime pair counting function. Okay, there's some deviation. I've proven that pi star of n increases indefinitely, but that doesn't necessarily mean pi sub n increases indefinitely. So what I need to prove is that the difference between these two functions is small enough so that we're confident that the prime counting function goes up indefinitely. All right, so I looked at how I derived this pi star of n, and what I did was I assumed that the number of pairs divisible by 3 is p sub n times 2/3. Okay, I approximated the number of pairs divisible by 3 by 2/3 times p sub n, and then I compared that to the actual number of pairs divisible by 3. Okay, and it turns out that the maximum difference between these two values is 2. Okay, and it cycles when the number of pairs is 3 or 6 or 9 or 12 the difference, the maximum difference is 2. And I'm excluding values of n that are divisible by 3. All right. Then I did the same thing with 5. I estimated the number of pairs divisible by 5 to be 2/5 times p sub n, and I compared that to the actual number of pairs divisible by 5, and the maximum value is 2.4. And this occurs at values of p sub n equal to 6, 11, 16, etc. Okay, so 6, 11, 16. And then I did the same thing with 7. I estimated that the number of pairs divisible by 7 is 2/7 times p sub n, and I compared that to the actual number divisible by 7. I ended up with this value here. The maximum value is 2.5714, etc. And this occurs when p sub n is 9, 16, 23, etc. Okay? And then I determined that the maximum error for any prime number is given by this equation. Okay, E sub p equals 3p minus 3 over p. So if p is 3, you plug 3 in there, you get 9 minus 3 is 6, divided by 3 is 2. So that's that. If for 5, I got 2 and 2/5, 2.4. For 7, I get 2 and 4/7. And for 11, I get 2 and 5/11, etc., etc. So to find the maximum deviation between my pi star of n and the actual prime counting function, pi of n, we sum up all these errors up to the square root of n, and I get the maximum difference. E max of n equals the sum of p sub 3, p equals 3 up to the square root of n of E sub p. And this turns out to be less than 3 pi of the square root of n, where pi is the prime number counting function. Okay. All right, so now I know the maximum deviation between my derivation and the actual prime pair counting function. So and this is what I got. This green line here is my pi star of n. The blue line here is the actual number of prime pairs that add up to n. And these red lines here are plus or minus E max. And you can see that the blue line lies comfortably between plus or minus E max. Okay. Now, if we zoom in on these on this region here, we see that for pi star of n minus E max, the curve actually dips below 0, but at the value of n equal to 622, pi star of n minus E max is greater than 1, and it never goes below 0 again. And this is because this E max of n is proportional to the prime counting function of the square root of n. So it increases at a rate less than the square root of n, but my pi star of n increases linearly with n. All right, so pi star of n increases at a much faster rate. Okay, so this proves that the Goldbach conjecture is true for all values greater than 622 or 628. And since it's known that Goldbach is true for values less than 628, then this proves that the Goldbach conjecture is true for all values of n. Okay, so in summary, I derived a function pi star sub n that is approximate to the actual prime pair counting function pi of n. And then I proved that pi sub 2 star of n increases indefinitely. And I proved that the maximum difference between pi star of n and the prime pair counting function is less than 3 pi of the square root of n. And since 3 pi square root of n increases at a much slower rate than pi star of n, this proves that there are, as n increases, the number of pairs that add up to n increases indefinitely, thus proving the Goldbach conjecture. All right. So here is a link to my paper. Please read it. It has all the nitty-gritty details that I did not cover in this presentation. And here are my other papers on other conjectures. Please make sure you're looking at the latest version because the previous versions did not have error analysis. Okay, and then here are my references. And thank you for watching this video. Take care.